Today we're going to be looking at linear motion with constant acceleration. You'll notice that that is different than what is in the notes in terms of it's not the right order. We're skipping the graphical analysis of velocity acceleration. I'm going to do that on Friday. So please be with me in the notes. We're at Roman numeral 2, linear motion with constant acceleration. Basically today what I'm going to be doing is giving you some equations that will allow you to take whatever data is given to you and find a way to work with it. And in order to start with that, a couple of conditions we have to lay down first. General information, we need equations that relate the quantities of motion. And the quantities of motion, now that we've dealt with all of this, are position, which we call d or distance or displacement, time, velocity, and acceleration. So we need equations that can mix and match those varieties of quantities. The limiting concept is that acceleration must be constant. And they'll make a big deal about this in these equations. It actually takes calculus to try to solve problems of this type when you have a changing acceleration. Acceleration must be constant. And you'll read that over and over and over again in these problems. Now, just to give you a peek of what that looks like, constant acceleration is going to look like this. If this is my velocity and this is time on my graph, and we'll talk about that more on Friday, then constant acceleration would look like that, starting at 0, of course, or it could look like that, or it could look like that. As long as it's a straight line, it's constant acceleration, because if it's a straight line, that means the change in my velocity over the change in time is always the same. My slope is the same, my acceleration is the same. I could even have this, and it would be constant velocity or constant acceleration. It would be constantly an acceleration of 0. A graph that does not have constant acceleration is going to look like this, where the slope is changing, or it could look like this. If I don't have a constant slope, I don't have constant acceleration, and I have to have constant acceleration for these equations. Now I'm just going to list the equations for you, how they actually come about and the algebra involved in deriving these equations. I've shown you in my completed notes on PowerSchool. I would encourage you to please look at those. It's actually kind of interesting to see where these equations come from. And first equation, number 1, is going to be A is equal to, excuse me, V minus V naught all over T. You've had this one before. And this is going to be a big equation in my tool chest. It's going to be a go-to a lot of times. But from that, I can get the equation, which is really the same equation, just written differently algebraically, but I like using it. V is equal to V naught plus AT. Especially I like this because I don't have anything in the denominator. If V naught is 0, then that kind of gets rid of a complication in the problem. So I like that one. But this one is entirely new, the next one. And it is D is equal to V plus V naught all over T, all over 2 times T. And I'm going to put this over 1 just so it doesn't look like an exponent. If I write it down here where you would normally write it, then it looks like it could be in the denominator. So I write it this way so you know it's T is in the numerator. You're multiplying it just across everything that you get for what's in the parentheses. And number 3, so this is, let me put a box around this. These are all kinematic equations, equations that you can use depending on what you're given. Number 3 is D is equal to V naught T plus 1/2 A T squared. Notice that the T is squared, not the A. There's not parentheses around it, only the T is squared. Here's another equation then for you to utilize if the situation is right. Number 4 is 2AD is equal to V squared minus V naught squared. So not there. Put a box around this. And you have a final 5th equation that you had from the beginning, and that's V is equal to D over T. This is actually a great equation. It's very simple, it's sleek. Use it quickly. It's a great equation. The problem is it's only of limited use. You can only use this if you have constant velocity, or you have average velocity. So feel free to use this under either of those circumstances, but only under those circumstances. Constant or average acceleration. All right, now you'll notice that what's nice about this is I don't have to have every piece of motion information in order to solve something else. For example, I can use this equation if I don't know anything about d, don't need to know anything about d. This equation eliminates the need for acceleration. This one, the need for v final. This one, the need for time, and this one is great, but you can only use it if you have constant or average velocity. All right, now the trick for success to these problems, I already listed for you at the very beginning of the homework packet. I'm going to state it again just so that you have this. First question you ask is this a 1 or 2 event problem? If it's a 2 event problem, where do they overlap? And I want you to look at number 9 in the homework. A bat flying toward a wall in a cave sends sound waves toward the wall. The sound waves travel at 330 meters per second, and the wall is 3 meters from the bat. If the bat is flying at 20 meters per second, approximately how far will the bat travel during the time required for the sound waves to make the round trip for the bat, from the bat to the wall? Notice that you have 2 separate events happening, and they're happening simultaneously. Sound is traveling at 330 meters per second. The bat is traveling at 20 meters per second. 2 totally different sets of data. They're both happening at the same time, but they're 2 different things. The same thing can't travel at 2 different speeds simultaneously. So I know it's 2 events. So I'm going to ask myself, well, where do those events overlap? And almost always it's going to be time. It was for that one. The time it took for the sound was the time it took for the bat to travel whatever distance. So usually it's time. That's going to be your go-to to look at, oh, do they overlap with time? Sometimes it's distance, but usually it's time. All right, the next thing you're going to do is you're going to read through the problem and you're going to write down your set of knowns and unknowns. And it's really important to include the unknowns. I'm going to make one up here. Let's say I read through the problem and I see that v is equal to 10 meters per second, and sorry about that, and v naught, they start at rest, so it's 0. D is 10 meters, and I want to know what's acceleration. Now, the first thing that's nice about this is meters per second, sorry. First thing that's nice about this is I can look at my units. It's all very visual. It's vertical. They're right next to each other. I can look at my units and say, everybody's playing nicely. We're good. The next thing I can do is I can look at the list that I've made of the variables, and I can find then an equation that's going to accommodate all of those. V naught, A, and D is the 4th equation. It's just so easy to pick things out if you do the list vertically. If you do it horizontally, it's just so much harder. So you're going to have to show me your knowns and unknowns in every equation. Let me step back. You're going to have to show me all your work, and that includes the knowns and the unknowns for every problem. And if you're going to have to do it anyway, you might as well do it in a way that works to your advantage, and that's vertically. And I already did letter C for you, where you pick the formula that matches. So here I've listed for you the set of equations that you can use. I'd keep that set handy, maybe write it on a 3x5 card, so that when you're doing the problems, you have that to look at right in front of you. All right, now what I'd like to do is try a couple of problems. First one is 3.6 from your class worksheet. A drag racer accelerates from an initial velocity of 0 to a final velocity of 40 meters per second in 80 meters. Calculate its acceleration, which is assumed constant. They're always going to tell you that. It's always assumed constant. So I'm going to write down what I know and what I don't know. It accelerates from an initial velocity of 0, v naught is equal to 0, and it has a final velocity of 40 meters per second, and it does this in a distance of 80 meters. And I am looking for, calculate its acceleration. I'm looking for the acceleration is, I don't know. Now I'm going to look right away. Do my units play nicely? I got meters per second, all in metric. I like it. Now I'm going to look at the set of knowns and unknowns, and I'm going to look for an equation that has V naught, V, D, and A. So it's 2AD is equal to V squared minus V naught squared. That's the equation that accommodates all of those. One thing I want to say up front with this is a subtraction sign. Leave that there. Don't square a negative out of it. Leave it as subtraction. That's going to become important. So I have 2a, and I don't know what that is, times d, which is 80, is equal to 40 squared minus 0 squared. I end up with 160a is equal to 1600. A then is equal to 10 meters per second squared. All right, and I'm not going to worry about you doing the showing the units in the problem itself. It gets too cluttered, it's too messy. We will step back a couple of times, not right now, but we'll step back a couple of times and say, all right, how did you end up with these units given the units that you started with? For now, if you know that you're in meters per second and meters, you know that your unit has to be meters per second squared. All right, 3.7. A sled on an air track at Holloman Air Force Base is used to test the effect of high acceleration on the body. If the vehicle starts from rest and accelerates to 50 meters per second squared, what is the speed after traveling 100 meters? And I'm going to start giving what I know and what I don't know. It starts from rest, so V naught is equal to 0. So the word rest actually means, especially if it starts from rest, means that V, or V naught, is equal to 0. If it starts from rest, V naught is equal to 0. Keep that in mind. And it accelerates, so I know A is equal to 50 meters per second squared. And it does it in 100 meters. So my distance is 100 meters. And it is asking, what is the speed at the end of the 100 meters? So V is equal to, I don't know. So I'm going to use that same equation that I did above. 2AD is equal to V squared minus V naught squared. 2 times 50 times 100 is equal to V squared minus 0 squared. When I do the math on this, and I'm going to leave it to you to figure the math out for this, well, I'll show you real quick. It ends up being that 10,000 is equal to V squared. So, of course, I have to take the square root of both sides. So V is equal to 100 meters per second. So I'm going to write this in here. It's 100 meters per second. And I look at the second part of it, still the same trip, the same thing, still accelerating. How much time is required for that same trip? So all of this data I can use because it's the same trip. So for little letter B, now I'm just looking for time is equal to, I don't know. I can use any equation except for V is equal to D over T. I can't use that because I've got two different velocities going on. I don't have an average velocity. I have a constant I don't have an average or a constant velocity. It's changing. But I can use any other equation that has T in it. And I'm going to use V is equal to V naught plus AT. It's just, to me, it's the simplest. V is equal to V naught plus AT. And the reason I like it is, first of all, because I have 0 in there that I get to cancel out. So it's 100, that's my V, is equal to 0 plus 50t. Okay, that one's pretty simple. T is equal to 2 seconds. Okay, now I'm going to do letter C, and letter C sets up a different situation. If the vehicle is stopped abruptly by an air compression ram in 10 meters, what is the acceleration when stopping? Assume acceleration is constant. So now for letter C, I know that my final velocity, it stops, so I know that V naught, or V final rather, is 0 meters per second. It happens in a distance of 10 meters, and I'm looking for what the acceleration is. I think that's all I'm given, so I feel like I don't have enough information. That's going to make me step back and say, what has the problem already told me? So I need to visualize this. I have, if I'm speeding up, let's say I go from 0 to 60 miles an hour, and as soon as I hit the 60 miles an hour, I slam on my brakes. The final speed of the acceleration is 60 miles an hour. What's the initial speed of my deceleration? 60 miles an hour. Because I accelerate and then I hit the brakes immediately. So my acceleration ends as soon as my deceleration begins. So my final velocity of the acceleration is my initial velocity of my deceleration. So V naught is 100 meters per second. And I am looking for A. So again, I'm going to use the 2AD. We seem to like this one. 2AD is equal to V squared minus V naught squared. So 2A times 10 is equal to 0 squared minus 100 squared. Now I want you to notice that it's 100 squared. It's not the negative 100 squared. Leave the subtraction in there. So important that you do that. You end up with 20A is equal to a negative 10,000. I divide both sides by 20, and I end up with A is equal to a negative 500 meters per second squared. Now, I would have predicted a negative for that because I'm slowing down. I'm slowing down at a ridiculous rate. But if you had squared this, you wouldn't have gotten a negative, and that your answer would not have been correct because the negative tells me it's a deceleration problem. Okay, so again, you're always given enough information. Sometimes you have to backtrack a little bit to see what it is that it's saying and dig that out. The next problem is number 30 in the homework. And just to show you how to set this up, I'm picking one from the homework. A Triumph TR7 starts at rest and accelerates to a speed of 27 meters per second in 11.8 seconds. Calculate the car's acceleration and then calculate the distance. So I'm going to first calculate the acceleration. I know that it starts at rest. V naught is equal to 0. V is equal to 27. And time is equal to 11.8 seconds, and I am looking for acceleration. A is equal to, I don't know. So I'm going to be using the V is equal to V naught plus AT to find my acceleration. So it's 27 is equal to 0 plus AT, so it's 0 plus 11.8 A. I divide both sides by 11.8, and A is equal to 2.29 meters per second squared. And then the question goes on to ask, calculate the distance traveled during that acceleration. So all of this data still applies. I have my 2.29 meters per second squared, and now I'm going to be looking for the distance. This is another one of those problems where I can use any equation that I want as long as I don't use the V is equal to D over T because my velocity changes. It's not constant, it's not average. I'm going to use D is equal to V naught T because that cancels out, plus 1/2 A T squared. That is 0 because my V naught is 0. So D is equal to 1/2 times 2.29 times 11.8 squared. And again, notice that it's just the 11.8 that's squared. And you get roughly 160 meters. You get somewhere between 159 and 160 depending on what equation you use. And you can try another equation and you're going to see you end up with the same answer. All right, and then finally, number 5. I wrote number 5 for you in the notes. I didn't type it out here because I needed the room. But I'm going to read it for you. Coach and his best wide receiver race the length of a football field. Coach runs at a rate of 14 feet per second, while his wide receiver runs at a rate of 17 feet per second. The wide receiver doesn't want to make Coach feel bad, so to end in a tie, he has Coach run a shorter distance. What distance should Coach run if they start at the same time? Now, hopefully you're seeing that this is a two-event problem, and the way they overlap is they're running at the same time. What do they have in common? Time. They're running for the same length of time. So two events, I'm going to set it up as actually two events. I'm going to start out first with the wide receiver and the information about the wide receiver. And the reason I'm going to start with the wide receiver is because I know a little bit more about it. If you'd started with the coach, you would have seen, yeah, I don't know anything about him. But I do know about the wide receiver, a little bit more at least. I know that his velocity, which is constant, it doesn't talk anything about acceleration, about V naught, V final. It just says he runs at this speed. He runs at 17 feet per second. And right now you're thinking, okay, that's all I know. But you know that he runs the full length of the football field. So you know distance. A football field is 100 yards. And of course, I'm seeing right away that yards and feet don't play nicely. So I'm going to convert it to feet. There are 3 feet in a yard, so I multiply 3 times 100. And I end up with 300 feet. And time is my overlapping factor, so I want to find time. V is equal to d over t, super easy. So 17 is equal to 300 over t. Remember that you get t out of the denominator by moving it over. So you divide both sides by 17. And t for both of them, because they're running at the same time or for the same time, is 17.6 seconds. Now for Coach, I know that he runs at a velocity of 14 feet per second. By the way, we don't mind that it's in imperial as long as we keep everything in imperial, so that's fine. I now know that the time is 17.6 seconds. It was the same for both of them. And the question was, how far does Coach run? So D is equal to, I don't know. Again, Coach runs at a constant speed of 14 feet per second, so I'm going to use D is equal to V over T. 14 is equal to the distance that I'm looking for, all over 17.6. You multiply those together, and D is equal to 246 feet. So he's running 54 feet fewer than the wide receiver, or he's starting 54 feet into the field as they start. All right, so I am going to have you guys do 31 through 39 for homework. And I do want you to know that this is important for the homework. When it talks about G's, G is an acceleration due to gravity, and the number for G is 9.81 meters per second squared. That's a piece of information you're going to need to know for the homework.